All right, so the last thing we're going to talk about is something called torque. So if we're talking about angular momentum, or I keep saying angular momentum, and we're not doing that yet. If we're talking about angular movement, or angular change in angles and angular dynamics, then we're not going to just talk about force. We're going to end up talking about something called torque, where torque is defined as the equation R cross F. So this means that since it's the cross product, I don't know if you remember how much you remember about the cross product, but you go out with R, you put your top two fingers out pointing in the R direction. You point F in the or you point your bottom two fingers in the direction of force, and then your thumb is going to give you the direction of torque. So in this case, torque, if we have a disk, uh, if we have a disk that's trying being acted upon by a force, and it's constrained so that it's going to rotate about some axis, then the torque is going to be pointing in this case up into the uh yeah, into the z-axis, into the sky. So that's all well and good. It's similar to the way that we defined omega, alpha, and theta to be just vectors that describe something while not really existing in the real world, which is there's a couple reasons for this, but they're going to be called pseudo vectors rather than real vectors. Pseudo vectors are virtual vectors. No, I think it's virtual vectors. I think pseudo vectors is a different thing. So they're going to be called virtual vectors rather than real vectors, because it doesn't like correspond to anything in the real world. And if you look at it in a mirror, then instead of uh, just being flipped along the XY axis, so like when you look at a mirror, your uh, side to side is going to be flipped, but not up and down. But if you look at a pseudo vector in a mirror, you see that the force is going to be pointing in the opposite direction. The and R is pointing in this opposite direction. So your pseudo vector is going to be pointing down rather than up. And then the magnitude of this is just R perpendicular to force, which is RF sine theta, where theta is not angular position. Uh, Theta is instead, sorry, I'm having trouble with the whiteboard again. It's just this angle right here, the angle between R and F. So what is torque? Like, why do we care? So basically, R cross F is going to be M R cross A equals MR squared, or no, MR cross alpha cross R, because A tangential is going to be equal to alpha cross R. And then there's a vector identity, which I am not going to get through, and I don't remember the specifics of it, even if I wanted to. But basically, R A cross B cross B cross C is going to be B times A dot C minus C dot A or no, never mind, that's the same value. C times A dot B, which is called back cab. Uh, so, so R dot alpha is always going to be perpendicular to each other because that's the definition of alpha. Alpha is going to be R perpendicular to both R and acceleration, the tangential acceleration. So M alpha R dot R, so R dot alpha is going to go to 0. So M alpha R dot R equals MR squared alpha equals I alpha. So in the same way that applying a force causes a change in acceleration, dependent on the mass of the object, applying a torque is going to cause a change in acceleration depending on the uh, moment of inertia of the object. So this is the main thing that you're going to get from here. Let me just save and uh, move on to the next part. So that's the main thing that you get from there. Force is like torque is just like force times R, and it causes a change in acceleration or in angular acceleration. So just like uh, we're starting to see a pattern here where all of these values, all of these things that we're talking about in uh, angular acceleration, angular dynamics are similar to things that we're talking about when we're talking about just when we're just talking about linear dynamics or like non-angular dynamics. So alpha, omega, and theta are similar to A, V, and X, as well as uh, a moment of inertia being similar to mass omega squared being similar to velocity. So I omega squared is going to give us K or the kinetic energy, and then R top cross F is going to give us the torque, which is going to be similar to uh yeah, the torque which is going to be similar to force. So I just have one more. I thought you were coming at 12 o'clock.
Oh, I was just joining the Zoom, that's all, just in case like you finished early and I can just go ahead and get started.
Oh yeah, I am at the very last part of it. So I'm on the last page that I'm going to do. So hopefully it shouldn't take more than like 10 or 20 minutes.
Okay, yeah, no worries. Thank you.
Mhm. So yeah, uh, we know that these are equivalent, so or these are similar to all these factors that we had in linear uh equations. So we just have the last thing that we need to do in order to like get a clear equivalence between torque and angular movement and kinetic energy is to just talk about the work. So work is going to be F dot ds for a uh yeah, it's going to be F dot ds for a rotating system. So ds is equal to d of uh theta cross r is equal to d theta cross r plus dr cross theta. And then theta, like I said before, like we were talking about acceleration and uh, radius, theta is defined to always be perpendicular to the radius. So this is going to become d theta cross r. Oh, so theta is perpendicular to the radius. Uh, okay, so theta might be perpendicular to the radius, but d theta d cross r and dr cross theta aren't necessarily. So the reason that we're able to cross this out is not because r and theta are perpendicular, but because uh uh yeah, but because dr is going to go to 0 because we're just worrying about the change in the angle, not the change linearly if you're going in and out of the circle. So ds equals d theta cross r. So omega, or not omega, w equals f dot d theta cross r, which is going to be uh, equal to, again, this is just a vector identity. This one I definitely don't remember how to do or how to derive, but if you need to, I can derive it on Friday. D theta r cross f uh, from, oh, this is just back cap again. Oh, no, this isn't back cap. A dot B cross C is equal to B dot C cross A. So if you want to, the way you can prove that is either using linear algebra or just basically going through both derivations or both cross products and seeing what pops out of the yeah, just seeing what pops out when you take A dot B cross C, set up the matrices, see what B cross C is, and then take the dot product of that for the vector, and then see what B dot C cross A is and see that. So this is d theta dot torque. So work is just going to be torque dot d theta in the same way that this is again analogous to what we were talking about earlier, where theta is analogous to x and torque is analogous to F. So when we take work equals F dot dx, it becomes work equals torque dot d theta. And then power equals dw dt equals d dt r torque times theta equals torque d theta dt equals torque times omega. Where this is only true true if torque is perpendicular to theta. I don't think they notice. Actually, no, that's yeah, if we have a constant torque, then work is going to just be, that's not true. Yeah, if we have a constant torque, then this just becomes uh t dot theta, t times theta. So d work equals ddt, d work dt equals ddt torque times theta. All right, so that's basically all I have to say this week. Hopefully it made sense. Hopefully everything's uh good and learned. This isn't really this is new material, but it's very similar to the old material. So I think if you have problems with this, then it's probably because you have problems with the old material. And I know I've said this after every section, but I'm going to be available all day Friday from like 9 to 5 or even later if you can't make it earlier. Just I want you guys to be prepared and I want to clear up any misunderstandings that you have. So that's going to be it. I'm going to stop recording. See you guys on Monday.